Hello everyone. In this video, let's talk a little bit about limits. Now, limits are one of the most important ideas in calculus. In fact, they're the idea that almost all of calculus is based on. But even though they're so important, limits are actually very simple. So let's take a look at them. Let's start with the notation for a limit. So a limit is notated this way. So remember that notation is just shorthand. So it's a shortcut way to write this all out. So we're going to start with LIM, which stands for limit. And then underneath, we're going to write X, and then an arrow. And this is going to go towards some other number, which we'll call C. The next thing we write is the function that we're taking a look at. So let's say f of x. The name of the function, f. It's a function with a variable x. That's why we have an x underneath our limit here. And this is going to be equal to some number, capital L, which is our limit. So altogether, the way that we read this notation, this says the limit as x approaches c of f of x is equal to L. And this notation, it's asking us a question. So what we want to find out is we want to find out what's happening to our function as the values of x are getting close to c. In other words, as my x values are getting closer and closer to this value c, what's happening to those y values? What are they getting close to? And that's what L is going to be. L is going to be that answer. So to illustrate that, let's take a look at a simple example. Let's start with something pretty basic. Let's take a look at the function f of x is equal to x plus 1. So this is a line. It's got a slope of 1. It has a y-intercept of 1. And let's graph this first. Okay, so here are my axes, our y-axis. This is also our function value, so these are our f of x's, and here's our x-axis. So our line has a y-intercept of positive 1, and it has a slope of positive 1. So here's a couple points for our graph. And we'll connect those together with a line, like so. Okay. So now let's take a look at a limit for this function. So let's ask the question, what's happening to our graph? So what is the limit as x approaches, and let's say 1, of f of x, and we want to find out what this is. So this is going to be equal to some number. That number will be the answer to our question. And that question is, as my x values are getting closer and closer to 1, what's happening to our y values? So in other words, on our graph, what we're looking at is as these values of x, so as we move along the x-axis and we approach this x value of 1, what's happening to these y values? So where's our graph going? So moving along our line, where's this going to end up? We also have to take a look at what's happening on the other side. So as my x values are getting closer and closer to 1 from this side, so moving from bigger numbers, and now we're approaching 1 this way, what's happening to the graph going that same direction? And as we can see, just based on this picture, it looks like they're both approaching the same thing. So on our graph, this point, as we approach from the left-hand side, our graph is approaching that. As we approach from the right-hand side, our line is also approaching that same value. So this point is the answer to our limit question. So it looks like this is the point 1, 2. So then our limit, so the limit as x approaches 1 of our function f of x, this is equal to 2. So in other words, as my x values are getting closer and closer to 1, my y values are approaching 2. And that's what a limit is. So what's happening to our graph as we get closer and closer to a certain point? Now let's take a look at an example that's a little bit more interesting. So let's do a new function, let's say g of x, and this is equal to x squared minus 1 over x minus 1. So a little bit more complicated. However, if we look at this, this can be simplified. The numerator is the difference of perfect squares, so that can be factored into x plus 1 and x minus 1. And this is still over x minus 1. And written like this, we can see that we have a common factor of x minus 1 that's going to simplify. So the simplified equation we end up with is y is equal to x plus 1, which is actually the same equation we had in our first example. However, because that common factor simplified out, what we end up with is a hole in our graph. So in our original function, I wouldn't be able to evaluate g of 1. So if I try and plug in g of 1, I would end up with 1 squared is 1 minus 1 over 1 minus 1, which is 0 over 0, which is undefined. So g of 1 is undefined. So we're going to have to keep that in mind when we graph this function. So let's graph this one. What it's going to look like, it's going to look like the line x plus 1. However, we do have the one little discontinuity at g of 1. So we have the y-intercept of positive 1. Now, normally I would go up 1 over 1, and we'd have another point here. However, at 1, our function is undefined. So to indicate that, we're going to put a hole. We have a little gap in our graph, and then we can keep going. So then continuing on with our slope, we can put another point here. And now let's graph this. So we just need to make sure that we keep the hole in our graph. So we can start from the hole and go this direction, and then on the other side, like so. Okay. And now let's ask the same limit question. So for this, let's ask, what is the limit as x approaches 1 of g of x? And what is this equal to? So again, we're looking for some value. What are our y values getting close to as our x values are getting closer to 1? So again, just to illustrate this, as we move along the x-axis, so as these values are getting closer and closer to 1 from this side, what's happening to the y values? So what's happening to my line? What's that getting close to? As I move along from the right-hand side, so as we approach 1 from this side, what's happening to the y values here? What are those getting close to? So as we talked about earlier, we do know that this function is undefined at 1. There's a gap here. But as we can see on the graph, from the left-hand side and the right-hand side, our line is getting really close to this hole. So even though there's no graph here, there's no point at 1, the limit of our function as we get really close to that still has a value of 2. So the limit as x approaches 1 of our function g of x, this is also 2, even though it's undefined at 1. So let's explain that one other way, is why this works out to 2. So what we're doing is we're looking at values of x that are getting super close to 1. So maybe we look at the value of 0.9, and we get a little bit closer, and we look at the value of 0.99. And maybe we get really, really close and look at 0.99999. What's happening to our graph when we plug those values in? So if we plug in 0.9, okay, where are we at on here? If we plug in 0.99, okay, how close are we now? If we plug in 0.99999, how close are we getting to 2? Same thing from the other direction. So maybe we'll look at values that are really close to 1 on the other side. Maybe like 1.1 or 1.01 or 1.0001. So if we plug in those values, what are our function values? How close do they get to 2? And as we get closer and closer to 1, the value of our function is getting closer and closer to 2. We never actually get to 1, so even though our function is undefined here, our limit is still 2. So let's define one more function. So let's say we have a function h, and then let's say this is a piecewise function. So the first part of our function, let's say this is x minus 1 for all the values of x that are less than 0. And then the other equation, once we get to 0, we'll switch, and now it's represented by x plus 1 for all the values that are greater than or equal to 0. Again, let's start by graphing this. All right, so to graph a piecewise function, we do have one switch here, and it occurs at x is 0. Everything to the left of 0, so all the values when x is smaller than 0, is going to look like this first line, which has a y-intercept of -1. Okay, but it doesn't have the or equal to part, so this will be an open circle here. And then we do have this slope of +1. So here are some points for the first half of our graph. And then once we get to 0, we're going to switch to the second equation, which is a line with a y-intercept of +1. And in this case, because it does have the or equal to part, we'll use a closed circle for that point, and then we can follow our slope of 1. Okay, so now that we have our graph, let's take a look at a limit question for this. So let's ask, what is the limit of our function as x approaches 0? So as x approaches 0 of our function h of x, what is this one equal to? So again, what we're looking at is as my x values are getting closer and closer to 0, what's happening to my values of h of x? So let's start from the left-hand side. So as I move along, my x values are getting closer and closer to 0 from this way. What's happening to these y values? So if I want to notate that I'm specifically looking at a left-hand sided limit, the way we do that, the limit as x approaches 0, and to indicate we're coming from the left-hand side, we're going to put a little negative sign in the superscript on the 0. So left-hand side is saying we're coming from the numbers that are smaller than 0. So this is the left-sided limit of h of x. And in this case, we can see that as my x values get close to 0, my values for h of x are getting really close to -1. Just like we saw in the last example, we don't actually get to -1. This piece of our function is undefined at 0, but we're getting really, really close to it. Now let's take a look at the right-sided limit. So as we move our x values closer and closer to 0 coming from this direction, what's happening to the y values here? So what are they getting close to? So again, we can notate that we're talking about a right-sided limit. So we can do the limit as x approaches 0. And now this time, to indicate we're talking about the right side limit, we'll do a little plus sign. So that's indicating that we're coming from the numbers that are bigger than 0. So the right-sided limit of our function, in this case, our line is getting really, really close to positive 1. So in this case, our two limits coming from either side of our function, they don't approach the same number. And if that's the case, we say that the limit does not exist. So that's the explanation of what a limit is. Again, it's asking us a question. As our x values approach some value, what's happening to our function values? We have a couple different possibilities, and maybe the limit doesn't exist. So this is just a description of what a limit is. We'll define a limit more formally later on, but hopefully this gives you some idea on how to use limits.